All right, let's get it started. Welcome, everyone, and thank you for joining us to this second virtual workshop in our webinar series titled Working Towards a Zero Waste World. The series is co-hosted by Boston University's Institute for Global Sustainability, Booz Energy and Sustainable Technologies Lab, as well as the College of Engineering at Boston University. Today, our topic is on sustainable materials and manufacturing. My name is Jörg Werner. I'm an assistant professor here at Boston University in the Department of Mechanical Engineering, the Division of Material Science and Engineering, and the Department of Chemistry. I'm also a core faculty member of the Institute for Global Sustainability that is co-hosting this workshop. Today's workshop will feature 3 speakers and panelists. First, we will hear from Dr. Toni Marechaux, a lead analyst at Booz Allen Hamilton. After that will be Dr. Tatiana Vakhitova, the sustainable lead at Ansys academic programs. And we will round out our series of talks with our very own Professor Benjamin Sovacool from the Department of Earth and Environment, who's also the director of Boston University's Institute for Global Sustainability. As an overview, each speaker will give a 20-minute presentation on their topic. After the 3 talks, we will have ample of time for addressing your questions in our panel discussion. To ask questions, please use the Q&A button of the Zoom webinar window that you're joining through. At any point during the presentations and the panel, you can input questions, and we'll get to as many of your questions in our discussions with the panelists after the 3 talks are over. Another quick note, the recording for today's webinar will be available on the website of the Institute for Global Sustainability at bu.edu/IGS. And the link will also be emailed to everyone who registered for this event. Now, before getting started, I would like to also welcome my co-host, Professor Uday Pal from BU's Department of Mechanical Engineering and Division of Material Science and Engineering. Now, with that, let's jump right into our first talk. Our first talk will be given by Dr. Toni Marechaux, a lead analyst from Booz Allen Hamilton. Dr. Marechaux received her undergraduate degree in metallurgical engineering from the University of Illinois and her PhD in material science and engineering from Case Western Reserve University. Her general interests are in abolishing barriers to new technology applications and engineering solutions for sustainable development. Dr. Marechaux applies her talents as a material scientist and technology strategist, currently as a consultant to the Advanced Research Projects Agency for Energy, also known as ARPA-E, in the Department of Energy in the US. Prior to this, Dr. Marechaux served as various roles as senior analyst and science advisors for, amongst other things, the Defense Science Board, ZIN Technologies, and supports of space experiment design, and as a board director at the National Academies of Sciences, Engineering, and Medicine. A lot of her prior work revolved around steel and advanced metallic materials, from mining to processing to applications, and she will talk a little bit about that right now. With that, I hand it over to Dr. Marechaux for our first talk. Please take it away.
Great, thank you so much, Gerd. This is a real honor, and I look forward to the discussion. And let's get started. I think many people involved in material science and in waste management know about the critical minerals assessment that the Department of Energy published back in July last year. And you'll see some interesting materials on here. A lot of prioritization went into this, and then there's one little mention of steel, electrical steel on here. But what's missing is steel. Why is steel not considered to be critical? Because, of course, we use it for so many things. We're certainly not going to build our I guess I'd like to argue that steel may be more important than all of these metals, but it is unfortunately taken for granted. And we're not going to build nuclear plants or wind turbines or even electric cars without steel. And so, just to give it a little more context, we mined, looking at all the metals we mined, this is Visual Capitalist, which is one of these terrific websites. I recommend it highly. Iron and steel are made 96% of all the metals we make and use, and iron is only about 2% of that, so it's really steel. But here's the interesting thing. If we also look over here at the industrial metals here on the right, for instance, There we go. Chromium. What is the number one use for chromium? It is alloying element of steel. What is the number one use for manganese? Alloying element for steel. Zinc is a coating of steel sheet. Titanium, alloying element of steel. Nickel, you think we make super alloys? Nope, alloying element for steel, mostly it's stainless. Magnesium. But even down in the precious metals, vanadium, number one use, alloying element of steel. Moly, niobium, tungsten. We do make some tungsten carbide, but even then, number one use, alloying element of steel. And so I guess I'll argue we probably wouldn't mine many of these steels economically if not for their use in steel. So steel is not just important. My argument, it's the only metal that actually matters. And I'll just give you one quick example of this. Floating offshore wind turbines. This is one of the big pushes these days for getting more electricity generation capability to power our upcoming economic transition to electrification. And just this is all the places that they've said have enough wind. This is not the offshore stuff that's sitting in shallow water. These are floating platforms in 1,000 meters or more of water depth, and they're more like oil rigs than they are like the wind turbines we think of today. But let me just give you a few numbers. The U.S. today uses about 4,000 terawatt hours of energy a year, electricity rather. This means we need about 30,000 of these platforms, plenty of room for them. You can see from the map. But each turbine will probably need around 3,000 metric tons of steel. And that would use maybe an additional 93 million metric tons of steel production. And we make about 90 million tons of steel per year in the US. So where is all this new infrastructure going to come from? What are our options? Well, can we mine more? The answer is, of course, yes, but it's also going to be very difficult. And one of those big reasons is ore quality. And so if you look at the United States started mining iron ore probably in the 1920s or so, usually up in northern Minnesota in the Mesabi Range through the Upper Peninsula of Michigan. But in the World War II, we mined all the, quote, good stuff. And now we mine today iron ore in the US that's down around 20% iron, 20% Fe. There is great deposits around the world. Brazil, Sweden have some amazing iron ore deposits, but they're just not as big. And of course, this little pink line from Russia, they're missing right now. They're not producing anything. This chart only goes through 2010, but you can see the trend is it's just going to get harder and harder. And of course, as we learned during the pandemic, domestic sourcing, very important. And of course, we all know that new mines and permitting and mine expansions are a real problem and also vaguely unpopular in many communities. And so there's the social aspect as well. So if we can't mine more, well, what could we recycle more? Well, of course, we can try to recycle more. There's a lot of steel scrap out there. But if we look at this, again, great diagram from the Use Less group at the University of Cambridge. If we assume that we are mining around, according to this chart, about, this I guess came from 2008, about 1 billion tons of iron ore, we can only add another maybe 10 or 15% of that from scrap. And that's all the scrap we have. Cars are not recycled annually. Buildings are certainly not recycled annually. Nuclear power plants, a lot of iron, a lot of steel goes into those things, not, they last for many, many years. So we're putting a lot of steel into the infrastructure. We're not getting that much back out. And what we're getting out, we use. So what are our options? And so, let me just talk a little bit about how we process iron ore today. As I said, we mine it in northern Minnesota. We blast it out of the ground. We shovel it into big trucks, big rocks. We take it to a beneficiation plant where we grind it up we crush the rocks into smaller rocks. We grind those rocks into basically sand. And we do magnetic separation. We separate the magnetite out from the hematite and then use various flotation technologies to either float the good stuff to the top or to the bottom, and then ship that off to pelletization. We make hard little pellets. These are about 1/2 inch diameter, very hard little rocks that we put into blast furnaces and into shaft furnaces. But the point that people don't realize about this is if you look at these first two steps here, we leave about 50% of the FE behind. This process is optimized for production for the blast furnace, but in the tailings piles, and this is, a lot of rock we take out of the ground, and we spend money and time beneficiating it, grinding it, crushing it, and floating it, we still leave 50% of the iron left behind because it's not economical for these two processes. So utilizing these tailings, waste reduction, is going to be very important. And again, let me just spend a couple minutes talking about how steelmaking works. This was a process, integrated steelmaking, that was developed in the early 1900s in England, moved to the United States in the 20s, where you take that iron ore concentrate out of the ground, you pelletize it into your little half-inch rocks, and you pour it into the top of a blast furnace, along with coke, which is, again, pelletized coal. And how that works is this blast furnace, I'm not showing you a real picture of a blast furnace. A real blast furnace is about 100 meters tall and about 20 meters wide. And you're pouring the coke and the iron ore pellets in from the top, and you're blasting oxygen from the bottom. You're not adding any other heat. There are no heating elements. There's no natural gas. There's no anything else going into this thing. It's basically like a big charcoal grill. Once you get it going and you keep adding more coke from the top and more oxygen from the bottom, you're just keeping that reaction going in an exothermic direction, and you're melting the iron ore and reducing the Fe3O4 to Fe2O3 to FeO, and finally to pig iron that flows out the bottom as a liquid steel. I'm sorry, liquid pig iron, which is only about 92% Fe. And so the point is that is really, really efficient. And it's going to be interesting to try and compete against it. And so we take the pig iron out. It goes into something called a basic oxygen furnace, where we also add scrap to it. We also add more oxygen. We clean up the steel. We help move more of the iron or iron oxide to iron, and then finally put it into a ladle. And the ladle is where we do ladle chemistry to make the iron or make the steel grade that we want to sell to a customer. And then, so this is about 70% of steelmaking worldwide. This is the process. But there's also something called an electric arc furnace. And this was developed in the 1970s by some very smart entrepreneurs who said, we have a lot of scrap. Why bother putting it in with all that other iron ore? We could just melt it directly in a big, basically, electric oven, a very powerful electric oven, and just melting the scrap. They said we can make some cheap grades directly from scrap. And that has evolved over time, that we make a lot of different steel out of electric arc furnace process. But we also, because scrap as a commodity isn't, you can't just melt scrap and get the same alloy out, because when you cut up a car or a refrigerator or half a building, you get a lot of stuff with it, and you tend to have to dilute that to get to the iron, to get to the steel grade you want, by adding pig iron to that, or something else to get your steel grade. And then, interestingly, there's a third process that is up and coming, DRI, direct reduced iron, that is a shaft furnace. This does have natural gas as a heating element, heating agent. Uses a slightly different grade of pellet, because this furnace can't deal with the same amount of slag or the same kinds of slag that a blast furnace can. And so you have to make your pellet a little differently. This produces not a molten steel product, produces a cold product, which we call sponge iron, which is kind of actually looks a little bit like a charcoal briquette. Those go into electric arc furnaces, again, about 92% iron, to bring up the chemistry to the standards that you need for a steel product. And so the interesting thing is this DRI process is right now only about 4% of steel making. And it's growing because it makes economic sense. And so the question is, are there other processes out there that we could start adding into this to give steelmakers options, to give perhaps to use some of those 50% iron that's still sitting in those tailing piles and not being used today. And so I'd just like to talk about some of the interesting technologies that we're looking at RPE and people around the world are looking at to try and figure out if we can do this better. So the biggest thing that people have talked about is electrochemical iron making. And this is, you you take your acids, you separate, you change the chemistry, and you can remove, you can separate the iron oxide, the oxide from the iron electrochemically. The problem, of course, is it tends to be slow. It tends to everything slower than a blast furnace, which is very fast. I just wanted to mention, blast furnace produces, a typical blast furnace will produce probably 80 to 100 ladles every day. And each ladle is maybe 250 tons of steel. So 80 to 100 ladles of 250 tons of steel for every blast furnace. This is going to mean a lot of electrochemical cells. And but this is we don't have to take over 100% of the steel industry. We just have to take over part of it. And so we're looking at things like, what if you could use a rotating impeller to scrape the steel off of the electrode to help you with your kinetics to get more reactants through the electrode faster. Other people looking at a colloid electrode. What if we could run something through the electrochemical cell that helps it react as it percolates through? And then another topic, of course, the acid-base generator. If we can pair two electrochemical cells together, that together will efficiently electrowin the steel. And those are just three. There are many, many more things out there that are they're trying to fix this or trying to find that next step. Let's see. When we talk about high temperature electrochemistry, the real challenge is that anode materials are generally consumable, maybe many times made of carbon, or prohibitively expensive. And so, what if you could use a liquid metal anode protected by a solid metal oxide, and you can ideally get your also maybe operate at a lower temperature, which is going to increase your efficiency. Another topic of great interest is a remote anode. What if you could just have your anode sitting above the melt and arcing down into the melt, and that preserves your electrode rather than sticking. What generally happens is in your molten iron, you submerge the electrode. And a third interesting idea is molten sulfide electrolysis. This is a really different process, uses a graphite electrode that is inert in this system. And this is a really interesting process because this probably is one of the only ways that we're going to be able to take copper out of molten steel. Right now, we just dilute the copper, and we're continuing to try to dilute the copper, and it's really becoming more and more of an issue. But this may be a good step that will solve some of those other problems. Let's see. Let's talk about some more novel iron production processes. People are looking at phytomining. What if I could use plants that accumulate metals and just put those all over where I have waste? I think I see a typo here. It's not solely, it is soil. But plants can accumulate metals. We know this. And what if we could find the plants that could efficiently accumulate iron? And, I think, I don't know if you know, iron is 4% of the Earth's crust. A lot of different places we could start getting iron from. Bioleaching is another really interesting topic. What if we could add biomass into the tailings piles, and that could dissolve the iron from the tailings? There's a lot of bugs that can do this. And what if we could just start draining off iron from the tailings? Ammonia as a reductant, another interesting concept. Instead of using basically carbon to carry our hydrogen for the reaction, what if we could use nitrogen to carry it? And this also helps with a lot of temperature control and melting and sticking and a lot of different, it really changes the process. It's very interesting. Let me see a couple more ideas. More directed energy, iron making. It turns out that if you could just add energy to iron ore, reach high enough temperatures, you can obviously separate the iron from the and in a vacuum, sorry, and separate the iron from the oxide. And you can do this with plasmas. You can do this with lasers. And it turns out that over the last, I don't know, few decades, both plasma generators and lasers have gotten far more efficient and far less expensive. They're really becoming industrial tools. And this becomes a really interesting option for iron ore processing that I don't think a lot of people have considered. And then finally, I wanted to mention, under the topic of process intensification, what if we didn't have to melt it at all? What if we could just grind up that iron ore into very fine powders, for example, mix it with in the right composition to reach the alloy we want into a bunch of different powders, mix it with a polymer binder, extrude it into the shape you want, and expose it to a flowing hydrogen stream. And it turns out that you can produce pretty good steel, thin-walled steel, but a lot of near-net shaped fabrication. Other people are looking at this same kind of processing to produce hydrogen, or rather iron ore powder. Things like additive manufacturing. So we have a lot of different ideas out there. And I just wanted to conclude by talking about all these novel processes, interesting ideas. What if we could pair these with new energy options? What if we could pair these with flexible iron sources, everything from the tailings to waste products from other mining areas? There's iron in everything. As I mentioned, 4% of the Earth's crust. Every waste product almost contains a lot of iron. Do process intensification throughout. I think there's a lot of options, and then we will be blessed with all the steel we need for our new energy infrastructure. And with that, I will hand over the reins to Kurt again.
Thank you very much.
Now I need to stop sharing. How do I do this? There it is. Sorry. Hi.
Thank you very much, Toni. We will keep the questions for our panel discussion afterwards. I would like to remind everyone that you can put your questions into the Q&A in your Zoom window, and we will address those in the panel discussion when all three talks are over. Now, next up, our speaker is Dr. Tatiana Vakhitova, the sustainability lead at Ansys academic programs. Dr. Vakhitova received her PhD from the University of Cambridge in the UK and has since been very active in the software industry. At Ansys, she manages a team of experts that are technically engaging with educators to improve sustainability aspects in engineering education. Dr. Vakhitova has also published numerous sustainability related teaching materials and has developed strategies for digital education content. Her current interest also focuses in the social life cycle assessments of materials. Without further ado, I hand the mic over to Dr. Vakhitova to tell us about Ansys grantor software for sustainable material selection and product design. Please take it away.
Thank you so much, Jörg, for introduction, and it was wonderful to hear Toni's talk. I'm looking forward to discussion. It's a lot I found out now about the steel and innovative processes. So in my talk, I will be describing Ansys grantor software and how it can help in material selection, and also our take on sustainable product design.
Tatiana, would you mind turning your video on?
Oh, of course, yes. I just was not sure if that's. Let me just find how to do it now. Okay. Maybe like this. 1 second, I'll just then. Yeah, here it is. I'm usually using Teams. It's different. Okay, so here we are. First, let's dive into what sustainability and how to assess it with the methodology by Mike Ashby. I'm telling you a bit more about who he is. Then Ansys grantor software solution, and then a little bit diving into simulation world. So I came to Granta Design when it was still Granta Design, and now it's Ansys. Initially in 1994, when University of Cambridge, Mike Ashby and David Sebon identified a great interesting new software for material selection. And this is something which was initially used for teaching, for education purposes. It's called EduPack, Education Package, Cambridge Engineering Selector, CES. EduPack was built on work by Mike Ashby, who is here in the picture. Mike is basically like the leader or the established the field of material selection. He published numerous books, and based on his work, the EduPack essentially was created, and methodology for material selection was developed in depth, and this was taken on board when the software was developed. Since at that time, there were other interesting solutions. One is for more industry, for research, Selector, and another one for materials information data management, MI. This is mostly for companies or for large research databases where researchers put their data on materials, on testing, and so on. So all the materials which is related to materials and properties and processes, which needs to have a home, combined with the in-house data by Granta. With this, it's a tool to manage this information and give differential access to the users. So since 2019, we are part of large Ansys company. It is engineering, simulation, software, and apart from materials, we have now access to huge portfolio of engineering simulation software from thermal, from fluids, electromagnetics, optics, and so on. So let's start discussion, and I would really like to hear some questions from you. So what is sustainable design, right? So probably it's design which supports our achievement, our efforts to get to the UN Sustainable Development Goals, right? It's a bit of short time left, but we would like to see some results there. But yeah, so let's say that sustainable design help us to achieve these goals. So how else we can look into that? This is something which comes as a background for 5-step methodology by Mike Ashby, and 3 areas we need to understand. So 3 capitals. There's natural capital as a concept. It's like clean atmosphere, fertile land, fresh water, productive oceans, healthy biosphere, and so on. Manufactured capital, built environment, industrial capacity, financial health. Human and social capital, knowledge, education, skills, culture. So all of these capitals can be impacted, right, or either positively or negatively. So we can say that environmental design or eco-design seeks to minimize the environmental impact on the life of a product, while sustainable design seeks to minimize the impact of the life of a product on all 3 capitals. In terms of 5-step methodology, which can guide assessment of sustainability proposals, we can take the following 5 steps, and more of this described in Mike's books. So if you're interested, we'll give you the link. The first, you need to identify kind of your proposal, your articulation for sustainable development. Let's say you want to introduce by 2030 or 2035 now so many electric cars on the market, right? And you take steps to understand whether this proposal is feasible and so on, whose concerns you want to address. So first, what's the proposal? How big? The scale? Thousands of cars, right? Or millions of cars? How soon? The time frame? Next step you are taking, and you're really looking at the stakeholders. Who will be affected? What are their concerns? What power do they have to influence this the outcome of this proposal? After that, the next step will be to uncover the facts about this proposal, or articulation in other words, and these stakeholder concerns, whether these concerns are justified, and what data we can find to confirm or disprove these concerns. Once you have the facts, you can understand what the impact on these 3 capitals, negative, positive, or neutral, and a reflection step will help us to understand if in the short term it's maybe impossible to achieve this? Can we do it in medium and long term? And what do we need to change to achieve that? Like, for example, infrastructure for electric cars, right? Took time to develop, but once it's there, people have less anxiety about the range, how long can this car drive? So just a bit unpacking this methodology a bit more. So these facts can help us with the proposal itself, with the stakeholder concerns, and identify information regarding resources, emissions required, regulations. And when you look at their impact on the free capitals, you understand more in depth what's the impact on the society, on the environment in terms of resource consumption, and in economics, costs versus benefits, what are the externalities, level of risks, opportunities, costs. And then with all this information, you can form a judgment, right? And at the end, you kind of interpret or make a synthesis whether the objective of the proposal is met, stakeholders' concerns addressed, energy and carbon efficient solution, and other things. So what are the hotspots, maybe social hotspots in terms of social risks, and so on. So that's the interesting way to look at it. As you're aware, sustainability is a very complex area, and many subjects need to be addressed. I found that with this method, it really brings the concerns of the stakeholders up front, and you kind of build your arguments based on what are important aspects identified for the stakeholders in question. So apart from that sustainability and sort of sustainable product design, we also look at what it means across the life of a product, right? It's not just that sort of aspect of what is now, but it's actually across the life. When you design the product, you need to look what are the environmental impact, economic impact, and social consequences this product has. So each phase of product life involves this flow of materials, energy, and money. And then it gets to the end of the first life, as you know from circularity agenda, that the first life is not the end, ideally is not the end for in majority where this is where we want to get to. But the product could be re-engineered, recycled, reused, repurposed, remanufactured, and so on. So there's definitely a lot of work in this space as well, how to make different circular business models and business strategies. So another level of considerations when it comes to sustainable product design, where this agenda is coming from, at which level it sits within, let's say, company, right? Sustainability considerations can be different levels. So one level is sort of more strategic, global view, where the company evaluates what are the risks, right, related to its activities, its business, its core business, what are the regulations, what are the requirements, for instance, net zero strategies, right? And what kind of other business models they can apply to make their business even more efficient in terms of CO2 emissions and still being profitable and socially friendly, let's say so. When it comes to sort of engineering view, and then we look at the evaluation of sustainability from the product perspective, sort of product level. And here we have absolutely it's impossible to not to take into account it's a performance, right? The part or the product which you create need to be safe, need to be functional, and it needs to be optimized from performance perspective. So you can only reduce mass so much to not to make it fail, this part, right? So optimization of the performance, and here you can also optimize the costs and environmental impact. And if there is an opportunity to also look at the social impact, and there's something which is let's say not mainstream, but with the new regulations, at least in Europe, European space directives, which require companies to report on this impact together with financial impact, it's very important, starting to be more and more important. So let's look at the global strategic level. So what kind of questions companies are dealing with? And this is something which is really connects to Toni's talk. critical raw materials, right? So you remember, Toni have obviously focused on the steel, and that's it's important, and on why. So critical raw materials, it's a group of materials with particularly high economic importance, right? And supply risk is also quite high if you're not the supplying country. So many countries now have different lists of these critical raw materials related to domestic supply, geopolitical situations, and also kind of economic strength, how good they are, the contracts they have, and opportunities to bring in new resources. So that could be something which is decided at this kind of more strategic level to understand the risk of supply of materials and to continue to develop the technologies. And for example, something you can create with the data we have, annual world production and the world reserves. So this is the critical raw materials from the European and the US lists. And that's actually every 3-4 years they are updated and changed the list as well. Another interesting area, and that's obviously something which relates back to this critical raw materials and environmental impact from this important materials for our renewable and clean technologies. For instance, neodymium has a large environmental impact. With its processing, there is a huge discharge of the toxic residue, and that's the picture from the region in China where there is a huge production of the rare earths. For instance, of course, it's not only environmentally. Well, the environmental consequence is that people who lived in this area had to relocate, right? Leads to social impact as well. Other areas where companies will be looking at is how fair, how socially positive is the supply chain, let's say. For example, there are some issues in different regions which violate human rights, like forced labor, where in this case, the local population is forced to work in some of the mines, and the revenues are fueling the conflicts in these regions. Why? Another interesting perspective on that, why it is difficult to mine cobalt, for instance, is also another important critical element for high-tech applications, and it's also from Democratic Republic of Congo. Because of the ore, right? The ore can have different sort of grade, and which is indicator of the abundance of each element, right? Extracted in the extracted rock, and cobalt has a varied grade, as you see here, which means that it's difficult to extract and process. So it's a difficult enterprise. It also involves lots of social impact, and there is a problematic area with cobalt and which actually required for our renewable future. So something to keep in mind. Another interesting visualization you can have with data in for instance, in EduPac and other solutions we have to explore sourcing and geopolitical risk level. Here is the annual world production and sourcing geopolitical risk, and you can see there's also immediately you can see where the materials sit, and here is very high for neodymium magnets, for instance, which we already discussed in some other. So obviously, for some countries which are producing these materials and elements, the risk will be lower, right? Another area, child labor in mines, which is very much now in media and so on, something which is happening still, and it makes so the conditions where people work and the child labor is used to extract metals In many cases, it's cobalt again mining. Yeah, it's something which we're trying to avoid, but also how to support these communities, how to support these areas where this is the only way how they can survive as well. So the data in our software in EduPack, for instance, also includes the nations of the world database, which we use to build our social impact audit tool. This is something in beta version, and this we are very happy to share if you would like to test it. And it helps to understand where this potential social impact, be that in this case negative, but sometimes, of course, we need to remember that it's also social impact could be positive because of the creation of jobs and other interesting factors which comes with a company operating, right, in certain areas. So we are very happy to share if you would like to, but I'm not gonna focus on it much more now because I wanted to give you a bit more perspective on the engineering view. And this is something which Ansys is very strong at. So when we look at the materials, it has this kind of, we call it triple challenge for sustainability. Materials choices are increasing dramatically. Materials information is very complex and it's difficult to acquire information from the supply chain. So sort of there are different first, second, third sort of supply provider or supplier, and that's information to get from the first level suppliers. It's sort of easy, and then the suppliers which supply to your supplier is already harder. Continuous increase in restricted substances, which we touched a little bit. Legislation is also dramatically increasing and changing. Requirements differ by geography, and essential to avoid huge costs to use the right material from the start. And it's estimated you can use approximately 80%. So it will cost you 80% more to change your design later. So yeah, and also product life cycles can be long, right? So you cannot estimate it easily at the start. So that's the kind of the areas related to materials. Where we are coming with the Ansys software and databases, they help to visualize the materials properties, help with the material selection, help with the understanding the environmental impact at each life stage of a product. This is something I will show you in a bit more details. We have more than 4,000 materials, sort of engineering materials, including technical, economic, and environmental data. Lots of records coming from a very established EcoInvent database, which are modeled and developed specifically for our needs here for these databases which we have. There are also data on restricted substances, which is connected to global legislation and directives. And of course, as a user, they can also input their in-house records and have a solution which is more applicable to their case. How are we doing with time? Probably 2 more minutes, right? Okay. So in terms of eco audit, as I mentioned, there is a way to do a very quick assessment, so-called streamlined lifecycle assessment with eco audit, which distinguish 4 life phases and transports. It gives you outcome with one resource and one emission, like energy and climate change, which gives you immediately, as a designer, you can see which stage of life of your product is the most problematic, right? And if you have a bit of a bigger picture, then you decide what they're going to do, whether you can minimize mass in your material part, or embodied energy, or maybe this is the issue with processing, or you can look at the transport and see what changes you can do there, or if it's the situation with the use, and again go back to your material and see where the thermal losses are or electrical losses. And then end of life, of course, you have a choice to try different things and see whether you have some potential to improve, use recycled material, and so on. So this is the strategy how you can use it with eco audit. So yes, I'm coming to the end of my presentation. The final slide I will leave you with, that's the more complex, and I'm not going to dive into now in all the details, but how we're seeing the whole, like, let's say, digital flow, where you have a material selection for your concept design. Then you go into your preliminary design, you apply your sustainability logic, you evaluate the risks. Then you go into detailed design optimization with the different packages of simulation packages, which help you to make it even more a specific part for your application, prototype and testing, which will be much cheaper because you already have the most advanced optimization, and production and launch. So again, at each stage, you can go back to materials and processes, and obviously have some more selection done in this way. Yeah, thank you so much for this opportunity to present what we do, and I will just leave you with lots of interesting things which we are doing. So that's the whole Ansys portfolio, and obviously I'm not going to talk about it today. Thanks so much.
Awesome. Thank you so much, Tatiana, for your insights and overview. Now, again, before we get to the questions in the queue, we will finish our last talk of today's workshop, which is from our very own Professor Benjamin Sovacool, a professor here at Earth and Environmental Science and the director of the Institute for Global Sustainability here at Boston University. Unfortunately, due to unforeseen circumstances, Professor Sovacool cannot join us live today, but he was able to provide us with a recording of his presentation. So I will get that recording set up to see the information that we need. A bit of background about Professor Sovacool. His research pertains to global energy policy and politics, energy security and justice, as well as climate change mitigation and adaptation. His research has been endorsed on the highest academic and political levels. He was, for example, a lead author of the Intergovernmental Panel on Climate Change's 6th Assessment Report, which was published in 2022. He also received the 2019 US ERN Prize for his work on social justice in the era of climate change and energy scarcity, as well as the Dedication to Justice Award given by the American Bar Association. Now, with that, we'll see if we can get that recording shared with everyone. And I'll leave it up to virtual Professor Sovacool. Peter, you might have to unmute or enable the sound. We cannot hear.
Everybody. I'm Professor Benjamin Sovacool from Boston University's Department of Earth and Environment, and it's really a pleasure to give this presentation on industrial decarbonization through a sociotechnical lens. And I wanted to start, obviously, by perhaps going through why industrial decarbonization even matters and is an important topic. I will confess that when I told my parents I had a new research project on net zero industry, their response may have been, "How boring." And I think many of us intuitively think that areas like climate mitigation for renewable energy or transportation or aviation are really exciting, but industry and factories that manufacture things are far less so. I've become convinced it may be something fantastically significant as a research topic. So I wanted to start with kind of what is it? And in this really nice drawing from a colleague, you can kind of see, well, it's basically about greening our entire supply chain. So we go from dirty factories, belching smoke and soot and pollution and carbon emissions with huge amounts of waste and huge amounts of toxicity and perhaps negative impacts on workers to a more resilient, decentralized, clean, green, renewable, and sustainable industrial sector. But of course, it's really easy perhaps to visualize it in a diagram. What might that actually mean in practice? So firstly, you might be surprised to learn on the right that industry, according to the US Department of Energy and the EPA, is currently the largest single source of greenhouse gases in carbon. It's actually 30.6% versus 30.3% for commercial and residential. The other really worrying thing is that it's also the fastest growing source of emissions. And these numbers also hold true globally, according to the most recent Intergovernmental Panel on Climate Change report from 2022. When you account for kind of the energy use needs, the heating needs, and the land use changes that are caused by industry, industry is also the single largest source of greenhouse gas emissions, ahead of everything else, ahead of just pure energy supply or land use change or transportation. So industry is the biggest source of emissions and the fastest growing, which makes it really a double challenge. It also makes it one where there could be lots and lots of activity and investment. The left part of this diagram comes from the International Energy Agency's net zero roadmap. They're looking out by 2040 and 2050. How many dollars do we need to invest in low carbon technology? And the numbers are amazing. By 2050, the IEA expects we will have to invest $110 trillion in net zero infrastructure, trillion with a T. The UN has called this the greatest commercial opportunity of our age. So it also implies that we have a whole lot of future investment and technology deployment, many of it, as you can see here, focused on infrastructure, electricity, and energy end use, which all intimately tie to industry. This is also from the US Department of Energy's Net Zero Industrial Roadmap, and you can see here how they're starting to talk about specific solutions that we can deploy. Places like Illinois, California, and Texas. Generally, it's carbon capture and storage, electrification, improvements in efficiency, whether it's energy efficiency, resource efficiency, material efficiency, and then low carbon fuels like hydrogen and potentially some forms of biofuel. The one on the right shows you the breakdown of industrial emissions by different subsectors. And here it's also not just about CCUS full stop, it's about CCUS deployment at very specific facilities, CCUS for chemicals, CCUS for refining, CCUS for cement, or food and beverages, or iron and steel, or things like glass and ceramics. So you're already starting to get a sense that the challenge, even though it may seem to have a narrow set of solutions, becomes more complicated. You have to deploy those solutions in many different types of facilities and many different types of places. And lastly, this is also from the US Department of Energy. This starts to get into more of their kind of 4 key pathways that they see for how to decarbonize our future industrial sector. And again, it gets into the types of CCUS, whether it's flue gas capture or doing direct air capture, which literally removes CO2 from the atmosphere and stores it beneath our feet. Or it could be different types of hydrogen, green hydrogen from renewables, blue hydrogen from natural gas, pink hydrogen from nuclear. You can see fuel switching on the upper right, which can include forms of efficiency, but also substituting gas or coal for gas, right? Or renewables for fossil fuels. And then lastly, we've got a lot of work on electrification, but also optimization and digitalization, where we make improvements into how these facilities can use electricity, especially renewable electricity that's either on site or perhaps that's actually from the grid in nearby areas with high amounts of wind and solar, geothermal, or hydroelectricity. Interesting though, as you probably can intuit, such a challenge does come with many, many barriers. And I'm a big fan of the Government Accountability Office. They did a report 2 years ago talking about the barriers to net zero industry in the United States. And of course, they identified 3 barriers, one of which was, of course, costs, because a lot of these options are still more costly than just the status quo. One of them was the need to roll out infrastructure, especially carbon storage potential and pipelines for things like hydrogen or carbon. And lastly, of course, community engagement and social acceptance. And any one of these barriers can be very significant. For instance, take infrastructure rollout. Currently, this shows you carbon pipelines on the left that exist in the United States as of 2023. We have about 5,000 miles. However, Princeton and others like the DOE are estimating by mid-century we might need 95,000. So we have to go from 5,000 to 95,000 in our generation. And that's just pipelines. It's one thing to put those numbers at you. It's another to see it. So see this map, existing pipelines, where the pipelines have to go. Existing pipelines, where we have to build the future pipeline network. It's almost like rebuilding the American interstate highway system, except in this time for pipelines. And that's just one of the many infrastructural challenges that face our engineers and designers, planners, and regulators as we really grapple with net zero industry. Maybe that's not surprising that when the DOE did an updated report, The 3 barriers now became 7. So the Department of Energy is even acknowledging there are 7 different barriers, from challenging economics, right, with difficult payback periods and uncertainties over the price of carbon, right, to kind of real difficulties with how these industries can actually implement a lot of these interventions, to over-reliance perhaps on hyped technologies like hydrogen and CCS, which are not yet proven at scale, right, to really a lack of value chain partners and skills and jobs, especially over pipelines and things like CO2 storage, right, difficulty in raising finance, difficulty and limited ambition among some states and regulators, and potentially a new Trump administration in 2025. And then again, really inconsistent public acceptance due to things like health risks and justice and equity impacts. And that's really where our work at BU fits into this, because we don't view industrial decarbonization as just a technical challenge. We view it as a socio-technical challenge. And that addition of socio really matters, because it's meant to unpack for a system like refining, not just the fuels and the refineries and the pipelines and the tankers, but also things like the business models, things like regulatory, fiscal, and policy dynamics, things like culture. What does oil mean to particular cultures like Saudi Arabia or Texas? What does it also mean about kind of user patterns of consumption, as well as market risks? You can also see a socio-technical system for food and beverages isn't just about the product that you're eating from McDonald's or getting at the grocery store. It's also about connections to land use change, cattle grazing, and agriculture. It's about, how we transport and store food, especially with refrigerants. It's about what does being a vegan or vegetarian mean? What is its cultural symbolism? It's about the products that we prefer, ready-made meals versus organic versus stuff from Whole Foods, as well as, eating patterns and household preferences. All of these matter. It isn't just about the product. And that's really how a socio-technical lens has a lot more analytical rigor and a lot more, I think, accuracy in explaining some of these challenges. And this is very, very different. This is from the US Department of Energy's net zero roadmap about how they view the challenge, right? They view it as it's about these 4 different types of pathways, and we have to basically just innovate our way out of the problem. Just like you can't solve war by more bombs, I don't think you can solve industrial decarbonization just with more technology. And that's really what a socio-technical approach is meant to reveal, is those non-technical levers, political, economic, cultural, that really shape and co-evolve with these technological measures. Another valuable thing about a socio-technical approach is it really helps reveal how particular vectors and sectors of industry become coupled. Sometimes people call this telecoupled to other dimensions. So hydrogen is a good example, right? Hydrogen doesn't exist by itself. It has to be made. It's an energy carrier. It can be in a fuel cell or in other forms. And it can also be from wind power, solar power, nuclear power. You can even have black hydrogen from coal and things like oil. Saudi Arabia is planning to have a lot of hydrogen made from oil-fired generators. So the different types of energy vectors can really shape the color or optimality of hydrogen, but so can coupling to things like water. You have large amounts of water that you have to either need to manufacture hydrogen, or that could be a byproduct, as well as things like steel, especially if you're using hydrogen for things like electric arc furnaces, right? Or for desulfurization, or for hydrocracking, or for ammonia. And it also connects to things like other materials like cement and glassware, and even transportation, right? We don't want to be shipping hydrogen halfway around the world like we do with LNG because of the energy intensities and energy losses involved. Same with cement and concrete. It is also coupled to slag and scrap metal and elements like terrestrial transportation and maritime transportation. And you still use a lot of fossil fuel stocks in the making of cement and concrete and mining. So the extractive industry sector becomes coupled in. This also implies that if you make improvements in one of these different coupled sectors, you can also help decarbonize the other sectors. So if we can perfect low carbon mining, that also is a gateway to making cement and concrete manufacturing more sustainable. The third thing that a socio-technical lens does, which I very much like, is it also enables you to find common leverage points or system dynamic points that can shape the entire system. So it becomes, a socio-technical lens reveals the complexity of decarbonization, but also counterintuitively, the simplicity of how some options can affect multiple parts of the supply chain at once. So in this study, We looked at what are called fluorinated gases. These sound very dry, but they're very important. These F gases are human-made, and they're some of the most potent greenhouse gases known to humankind. 1 ton of sulfur hexafluoride is the equivalent of more than 22,000 tons of CO2. And SF6 is used in Teflon, it's used in silicon etching, it's used in race car tires, it's used even in some tennis shoes, or at least it was. And so these kind of manufactured F gases, because we made them, they don't degrade in nature. And it turns out they're in a variety of things, from electronics to medical dose inhalers to military radar systems, even to forms of air conditioning in our cars. And while that is a hugely complex supply chain and differentiation of products to decarbonize, our review actually found that just 4 innovations, 4 things could basically get you almost 80% decarbonized for F gases. If you did better monitoring and leakage of and training, if you looked at low greenhouse warming potential substitute gases, if you really ramped up efficiency, and if you really dealt with waste, or even better yet, reuse, those 4 things can basically help decarbonize much of the F gas sociotechnical system. And then for maybe a more concrete example, for cement and concrete, you can also see here, we basically have 4 colors of options that also can decarbonize many, many pieces of the cement and concrete supply chain in one go. Whether it is at the top in red, improvements to efficiency and waste recovery and waste-derived energy, or in the second one in orange, if it's things like dematerialization and recycling and resource efficiency, or look at the big role for carbon capture and utilization, or carbon capture and storage, and then finally how we digitalize and make more efficient or different processes. Again, these 4 innovations can help you decarbonize multiple parts of that very complicated, intricate sociotechnical system. And lastly, had to throw this in here because I'm a social scientist and we love our theories. There are a number of what are called sociotechnical theories, heuristics, conceptual frameworks, and analytical tools that exist. How many we didn't know, so I did a study here with Marechaux and Jeremy, where we asked prominent experts in the field what theories are most relevant to industrial decarbonization, and we were blown away. We discovered 88 theories, 88. Whether there are a handful of core theories, which are explicitly designed by researchers to deal with how we understand and predict industrial decarbonization, or semi-core theories, which are more about industrial change, although maybe not necessarily about decarbonization. They could be about industrial transitions more generally. And finally, peripheral theories are about industrial society relations at the most general level. And within that, we identified many different families of perspectives, all sociotechnical, but all of them view the kind of fundamental drivers or elements of foci as different. Right? A theory of sociotechnical transitions might talk about the coevolution between new innovations called niches and the dominant regime, and how incumbents manipulate the landscape to tilt innovations in and out of their portfolio, which is very, very different than, say, a theory of ecology, which views organisms that have a metabolism and they kind of compete almost like in an ecosystem, and some of them may actually become extinct or become co-opted and copied by other species or innovators. To still others like justice, which is really about just transitions, equity, and how we actually minimize disparities among very, very vulnerable groups or vulnerable places and spaces like the Rust Belt in the United States. And what's also fascinating about these sociotechnical theories is many of them are what are called multi-scalar. So all the ones in gray here are meant to actually couple together and explain phenomena in multiple scales of the decarbonization challenge. It isn't just about individuals and employees at firms. It's also not just about neighborhoods or supply chains. It's also not just about cities. It's also not just about nations. It's also not just about global governance architecture. It's about all of it together. And we have some actual theories like the political economy of decarbonization or the multi-level perspective, which are intently there to help explain these multi-scalar phenomena. They also really hedge against our analysts that only look at one scale. Another thing that these theories do is they have very different temporal explanations. These are called phase models, right? So they see time in very different ways. And I've just plotted here, we plotted here, just 8 of these kind of archetypical timelines And each of them, look how non-linear they are. Look at all of the punctuated equilibria in many of the curves. And also look how no one is the same. So each of these theories also envisions that process of industrial change as a very different phenomenon. So we have a very rich array of heuristics and theories that we can use to help understand decarbonization. We can also learn from other countries like the UK, and I am an American, so anytime I'm praising the UK, they must really be worth it, since we did fight in a Revolutionary War against them. The UK has really done a very holistic socio-technical policy mix for their industrial decarbonization. And in 2022, I would probably say they may have even been the leading nation in the world for their efforts to decarbonize industry. You can see here, I know it's hard to see some of them. They have a Climate Change Act, which implements a carbon budget. They also have carbon taxes and a cap and trade system. They have different types of demonstration funding for innovation, for net zero, for transforming foundational industries, and even an industrial decarbonization challenge, which actually funded one of my grants, which got me studying this, alongside specific incentives for hydrogen and renewable heat, as well as even work on demand side behavior. So again, multiple pieces of that socio-technical puzzle are all targeted with the UK's approach, which is also very phased and staged, and it gives a clear roadmap. And I really love that it puts efficiency first in green, which includes a variety of issues dealing with waste and implementing more efficient feedstocks, digitalization and heat recovery, coupled with carbon capture and storage, coupled with fuel switching for things like hydrogen and renewables and electrification. You also can see that they're really focusing first on lower rent actions that'll be done now to the end of this decade before they get into some of the more uncertain ones that may have a little more innovation to occur and are lower on the TLL roadmap. And all the while, the importance of a socio-technical approach and the UK's approach is it really recognizes that these non-technical dimensions are as important, maybe more important, but I'll say at least as important as the technical ones. And to put that into perspective, this lovely diagram is from the Rocky Mountain Institute. It's from this year. And what they're mapping here is just the simple stakeholder diagram for the deployment of a hydrogen hub. So this is just one piece of the socio-technical system. Look at all of the primary, tertiary, secondary, and other stakeholders involved. Look at all of the arrows of multiple levels of engagement, and everywhere you see a lightning bolt is some degree of conflict. And this is just to approve one hydrogen hub, right? So it is an intimately socio-technical system involving the media and academics and labor unions and projects and finance and governments and NGOs and environmental justice groups all together. So I think this kind of socio-technical approach helps reveal, quite honestly, the breadth of the challenge in front of us, but also lets us adequately grapple with those many specific dimensions we have to harness to address the problem. Thank you.
All right. With that, we thank Benjamin for his virtual talk, and we ask all our speakers that are here live to rejoin and get our panel started, for which we have a little bit of time left, so that's great. And we'll get started. We saw some questions we already answered throughout the talks. So maybe I can get us started, and I'll start maybe with Toni, since you were our first speaker, with a question for you. I was amazed by the breadth of technologies that are being proposed, or approaches that are being proposed to extract iron in various ways, including biological, plant-based extractions. Is there of any of these a particular area you can point to that says it's like, this is the presence of iron in a certain area or material that would really benefit from one of these extraction methods? You're still muted.
Well, there's obviously many. A big one that people look at is red mud, which is the waste product from aluminum processing. And we have big lakes of that in the United States that are pretty toxic, and nobody knows what to do with them. And so there's an area where I think biology could be a thing, although, everybody's looking at other ways to do it too. So there's, like I said, everything's made of iron. If you look at copper tailings, they're 60% iron. You look at, iron's always that pesky thing that is left at the end when you take the other metal out.
Gotcha. And the way I traditionally, at least as a academic that doesn't know much about industry, looked at it, industry always, to be able to scale things up, looks for one solution that they can apply broadly to everything. So this large set of potential solutions, while it makes maybe technological sense, do you think there is a path towards an actual diversified iron extraction industry?
And I think so, because it's so big, that modular approaches can help. And so, right now we mine iron ore in northern Minnesota. It goes on big barges, travels by rail or truck to Duluth, gets on the boats in the Great Lakes, and you either put steel plants today are either where the iron ore is or where the iron ore can easily get to on the lakes, so Cleveland and Buffalo and Chicago, or where the coal is, which is why there's a big steel industry in Pittsburgh. And so if we can start making things more modular, using electricity, using especially modular electricity, there was just a study put out, I think, earlier this week on if we do electrify all of the steel industry, how much electricity we're going to need. And so there's but a lot of different ways that it can go. All of the technologies that RPE is funding, one of the requirements for the program was the potential to be able to scale it up to 15 million tons a year. And if we can start putting many different technologies in, because there's so many different sources of iron in so many different ways it might work, that would really address a lot of the challenges that the industry faces.
Thank you.
Uday, you're muted. Still muted.
Yeah, I think the scale of the problem that you just mentioned is really mind-boggling. I mean, you said we are producing close to, in the US alone, about 100 million metric tons.
About.
Right. And then if we go to, say, if you want to go to renewable energies, the infrastructure that we need and the material that we need, we may have to scale this to twice as much, right? Something like that. So I just
let me just mention that many electric arc furnaces, most are the largest electricity user in the state. So we use a lot of electricity today in steel, and we'd like to use more.
So if we go to, say, if you want to double the steel production to build, say, a renewable energy infrastructure, be it wind or, say, nuclear or what have you. So right now, what is the rate of growth of steel production? I mean, at what rate is it currently growing? And then to compare that with what you'd like it to be. I mean, that really is going to...
It's really a question, because, the various organizations have put out estimates for where they think it's going, and it either is the same or less, or double. So it's, China is by far the largest producer of steel, and they have been for a long time. And I think everybody has, maybe looked at the fact that growth in China has decreased lately. And so their steel production has also decreased. Will that stay the same? Nobody really can predict very well. But if we want to, expand our nuclear capabilities, if we want to expand our wind capabilities, especially domestically, we're going to have to increase the amount of steel we produce domestically as well.
Yeah, I mean, that really says a lot as to why we need to invest in technology, in steelmaking technology, really. Yeah.
And maybe along those lines, I can bring in Tatiana here for this discussion. You mentioned that a critical piece of designing and planning in the material space is the supply chain question. So one thing I was wondering is how much how quick changes, how large are the fluctuations over, the years and decades that we have seen and that we might be seeing in supply chain? You sometimes hear like, yeah, things happen, but the one thing that's always flowing is oil, right, from various countries. Steel now, we just heard China used to be the biggest supplier. It's changing. Is that something that fluctuates a lot and can easily be even predicted if we're thinking about a product?
Well, it's a very good question, and I'm sure there are, the people who are dealing with their like trade materials they will see the price fluctuation, right? So in our case, I think the best way to address it would be from the critical raw materials perspective, because we see that there are more materials and they're changing as well. Every 3-4 years, when we have a new list, we have new materials on this critical raw materials list. For instance, in European space, I think in the US, you also have changes, right, on this list. So that means that those materials with economic importance and large supply risk are also moving on this table. So I cannot give you in-depth kind of data on that, but looking at the regulations and something which is very visible now with the Critical Raw Materials Act being introduced this year as well, this is something becomes much more prominent, and obviously geopolitical situation influences this and moves people to realize that there should be some framework which supports companies who need to protect their supply chains and support them with their strategies. And I know with this Critical Raw Materials Act, for instance, it's prioritize projects which are related to processing or to recovery or to producing of these critical raw materials in that region where the act applies. So yeah, so there is a movement. There is definitely change of what's there, but some of the materials are staying there, so it's not changing. It's still important for our renewable energy.
Tatiana, you started with the sustainable design paradigm, improving the social capital, manufactured capital, and the natural capital. Sometimes when you do this analysis, it might show that your natural capital may be improving, or your manufactured capital will be improving, but your social capital may not, right? So how do you quantitatively or logistically assess the relative importance of these three capitals to figure out what is a sustainable project, for example?
This is something very interesting as a sort of discussion in the literature as well, and I would relate it to life cycle sustainability assessment literature, where people are trying to combine ELCA, environmental LCA, social LCA, and also life cycle costing. I actually very much like the way how Mike Ashby is actually taking it. He proposes the way to apply to the framework indicators, because each life cycle assessment could be quite detailed, very large, and it takes several months, right, to do it. So imagine how complicated it is to combine them all in something which will give you life cycle sustainability assessment result. So in his latest work, he introduced more sort of framework indicators for each of these ELCA, SLCA, and LCC assessments, which gives you that result, which you can then combine compare to products, for instance. So one of them will be, let's say, higher, better performing on social parameters, another one on environmental parameters. But then the question is really how you approach that, right? How you approach, which product to choose. Let's say one scores better in social impact, another in environmental. And we discussed this topic with him, and basically we the conclusion is essentially it comes with which hat you have on, so to say. Either you come from the environmentalist perspective, you will prefer the product which has more environmental credentials. If you have more of the, like industrial, let's say core industrial perspective, you prefer the one which has more profit. But between environmental and social, it's sort of philosophical aspect as well. So which standpoint you have, and which sort of, are you more liberal or conservative? And then it becomes kind of question of where your values are, what is your preference, and as a company, where are you standing? This is something which is maybe social scientists can help us answer, which is unfortunately we don't have our colleague, but I'm sure he will have lots of ideas there. I was really enjoying listening to his talk and looking at the life cycle assessment there in one of the corners with a techno-social approach. So in short, it really depends where you're coming from. My answer.
Yeah, the easiest thing would be like if it benefits all three capitals, then it's a no-brainer.
Yeah. Well, the thing is that sometimes it happens. Sometimes it's benefits really. They're environmental, let's say social, right? The better environment will help health, right? So you have that intrinsic connections, and the most interesting things are happening actually in these connections between capitals, and how you can bring them all up, which is the interesting challenge to have.
And I think you brought it up, and I like that you mentioned often that the stakeholder, which can be various, they should have to be brought up front, right? What are the impacts and the benefits for certain stakeholders? And I guess one part, certainly on the social side, that you hear often is kind of a little bit of a dichotomy between, having a new technology, new production, new mining even, or energy resourcing in an area brings jobs, right? That's a social benefit. That's a benefit for the community living there. While the negatives are often the questions around environmental pollution, around these kind of things. And not just between the individual capitals, but even within a capital, there's a lot of balancing being done. And especially on the social side, I wonder, how much even communication around certain topics matters, right? There's perception, and there's worries about certain aspects, especially about the unknown and the new, that might be, the risks of those might be mitigated by, of course, good regulation and policy, but also by good communication.
Yeah. And how actually companies behave in the areas where there is a social situations, like whether we know the example of Fairphone, right? They do operate in Africa and China, but they're trying to find the suppliers which conforms with their requirements to how they want to see their people are treated and their processes are. So it's also which position the company takes and how they will be required. What requirements to their sustainability strategy.
And then maybe to connect a little bit, materials choice and steelmaking, and Toni, maybe towards you a little more. You showed us, we're using so much steel. We use it apparently very long. My first question when you started was, how much do we have that we can recycle, right? It should be somewhat straightforward, but it sounds like, no, we just keep building new stuff. There isn't that much old stuff coming, back to the pipeline. But how much opportunity is there to replace steel in certain areas where we just use steel because it was there, works well, but there's, equivalent or sufficient replacements, including things like wood, right, in construction that we could use?
No, I mean, we use steel because it's inexpensive, number one. And it's available. But there's very strong wood, and wood has the advantage that it's a carbon storage in wood, and there's a lot of great technology going on there. If you look at the RPE Hestia program, they're doing a lot of great work in that area. But I think there's a lot of ways we can think about to use less steel, stronger steel. There's just there's always a material substitute that you can use.
Yeah, I would like to answer that question by saying, 1 pound of steel is like maybe 10 to 15 cents, and think about 1 pound of water. just compare the two. It's very hard. The property and the cost, steel is unbeatable. One question that I have for you, Toni, before we end, is that the electric arc furnace, in my mind, it gives the steel an opportunity to have a circularity, right? The electric arc furnace is fed by the scrap as well as the things from the DRI. But the DRI is sort of limited in terms of many of the challenges. So right now, we don't have any of the advanced technologies that you have mentioned at scale, commercially, right? So
we have two that are close, and those
Okay.
two many people have maybe heard of. The two largest efforts in the U.S. are Boston Metal, which is looking at high temperature electrolysis with an inert anode, and Electra, which is out in Colorado, which Boston Metal's in Boston. Electra is looking at a low temperature electrolysis process, and they're specifically partnering with Nucor, the largest electric arc furnace company in the U.S., to provide them with pure iron to put into their melts. So there is progress. We think it's coming. I'm really interested of how Ansys and Granta will include all these new steels and how they will value them in their software.
Me too. I'll check with our data team.
That will be something for the future, because this brings us to our end. Thank you, everyone. We did reach the end of our workshop today. I would like to give our speakers a virtual round of applause. Thank you very much for taking the time and presenting to us and having this wonderful discussion with us. I'm sure everyone was applauding that we can't see in this webinar. I would also like to point everyone to the website of the Institute for Global Sustainability, where you can both register for our last workshop in this series, which focuses on decarbonization through carbon conversion or CO2 conversion. You can also find the recording there for today's webinar, and the link to the recording will also be sent to all registrants, and you will be able to access that and watch it later. Now, once again, thank you all for attending, and a big thank you to our speakers and panelists again. I wish you all a wonderful weekend, and if you are in the US, I wish you a happy Thanksgiving next week. And that concludes the seminar. Bye, everyone.
Thank you and bye.
Thank you. Bye.
Bye-bye.